All right, thank you very much. Thank you for your patience, and it's great to be here today. So my background is formerly in reinforcement learning. So I think one of my jobs today is to sort of get you excited about some of the things I care about and tell you some of the challenges in that field. So let me start with sort of, when I think about model-free control, the kind of problems I have in mind are fairly wide-ranging. It could be, as simple as, deciding what you want to eat for dinner, or it could be, sequential decision-making for clinical treatments, optimizing a power plant, optimizing energy grid, or of course playing Go. And so my special interest is in games, computer games, classic games, and the reason for this is because reinforcement learning has been really successful at playing games. And so some of the examples here you have is from 1956 is Samuel's checker player, which was actually using a very clever form of reinforcement learning that was sort of reinvented later on called TD Lambda. And then backgammon, of course, which was probably one of the first successes of neural networks with reinforcement learning by Jerry Tesoro in '92. And more recently, there's been a spate of interest with some high-profile successes, in part from us at DeepMind. 2015 we had a Nature paper on playing Atari games, and 2016 we also had a paper on, of course, superhuman Go playing. So just to give you a sense, this is a PDF, so unfortunately you won't get the video. Just to give you a sense for why this Atari business matters, if you haven't heard about it before. So the Atari 2600, of course, was a computer, a video game console that was developed in the 70s, and came to be sort of a flagship of experimental work in reinforcement learning. We had a paper in 2013 that proposed the Atari 2600 as a platform for effectively reinforcement learning research, but also more generally for artificial intelligence research. And the reason for this is because of, it's a challenge domain. So what challenges it pose? Well, first of all, what we said is we'd like to play these games, so develop controllers that can play these games using joystick motions, okay? And really playing the game. And what that means is playing the game from pixels. So the agent observes a sequence of images, of frames, and each image is 210 pixels by 160 pixels. And the agent observes this at 60 frames per second. So the setting that I'm going to be in is discrete time, high dimensional. And the reward that the agent is getting at each time step is the change in score. So we're playing a game, so we want to maximize this sum of discounted rewards. In this case, it's going to be trying to maximize the score of the game. All right. So to give you a sense for the kind of domain I'm usually looking into, it's going to be very high dimensional. In this case, there's 33,000 discrete dimensions. Each dimension is a pixel with 128 color values. And an episode is going to last up to 30 minutes. And if you do the math, that's going to be about 100,000 decision points. Now, the most interesting thing about the Atari is the fact that there's not one game or two games we're trying to solve or get good controllers for, but there's over 60 of them. And what we're looking for is an algorithm that's going to be able, or an architecture that's going to be able to play all of these games without changing the actual parameters, the hyperparameters of the algorithm. And each of these games is quite diverse. I won't be talking much more about this today, but you can think of games ranging from Space Invaders to Pong, to maze games to Pac-Man. So we really have to look for a learning algorithm that's robust to all this variation. On the other hand, we have the incredible success of deep learning. And that started, I think, now 5 years ago. Deep learning has been around for quite a while, but the success story started 5 years ago when Alex Grzechewski and his co-authors showed that you could get state-of-the-art or beat state-of-the-art classification on visual tasks simply by using deep learning. And what this talk is about is sort of talking about the basics of reinforcement learning and the basics of deep learning and asking the question, how do they combine? right? And so one thing that I really want to emphasize is the kind of work I do is to look at theory and to look at practice and ask the question, how do we bridge the gap between these two? How can we come up with algorithms that are well motivated from a theoretical perspective, but are also going to stand muster when we take them to play Go, or take them to play Atari, or try to optimize a windmill farm, for example. Okay, so when I say model-free control, I'm going to come down to that point a bit later, but I want to say for now, where has this kind of technique been successful? And there's a few sort of key ingredients that keep recurring. One of the things is often the dynamical systems are very complex. We don't know how to write them down. If I think about an Atari simulator, I don't have a model of that. All I can do is take the simulator and simulate it forward. And these samples are fairly expensive, right? So I can't generate millions of trajectory per minute. Another ingredient is often the state spaces are going to be quite high dimensional. If they're low dimensional, we know we have really good solutions that are going to scale much better or have much better guarantees, right? So 30,000 pixels for me is going to qualify as high dimensional. A third thing is often going to be long time horizons. From a discrete perspective, that just means we don't quite know where the decisions are happening, and we need to potentially make a different decision every time point. As an aside, I think this is actually a place where continuous time methods might shine, where you, instead of trying to deal with these long time horizons, you approach them from a different perspective, the continuous time perspective. And finally, surprisingly maybe, one place where model-free control has been so successful is all these domains where there's an implicit opponent. So these are not technically environments in the traditional reinforcement learning sense with a Markov process, because there's an opponent that's trying to typically minimize your payoff. But despite this, these model-free methods tend to be really good in these circumstances. So Go is an example of this. Backgammon is an example of this. Poker is also an example of this. And why that is, I think we don't know, but maybe it has to do with the complexity of these problems. So suppose you want to use model-free methods or reinforcement learning methods in your problem. What are some of the questions, some of the practical considerations you might have in mind? Well, first of all, you should ask the question, are the simulations reasonably cheap? Because I'm going to operate under your assumption we don't have a model, and so if the simulations are extremely expensive, you might want to build a model instead and not use model-free methods. Okay. Secondly, is the notion of state complex? If it is, then we probably can't model the state easily, so we'll have to use some sort of approximation. Third, is there partial observability? So is the state not actually a Markov description of the world? And if that's the case, we've had good success with model-free methods, even though they're not actually guaranteed to converge. But then, if we answer yes to the question, can the state be enumerated, then maybe we need to move away from model-free and into something like value iteration. And if there's an explicit model available, I certainly think we can do better than model-free methods. So this is just to say, model-free method is not the end-all of all the solutions. Okay. So what am I going to talk about in this talk? It's going to be very simple. I'm going to go from the ideal case, the way we typically do the theory in reinforcement learning, and then move towards a practical case, which is normally the setting that we're going to consider when we have to deploy these algorithms on problems. So let me start with a quote by Sutton and Bartow from the reinforcement learning, the canonical reinforcement learning book, An Introduction to Reinforcement Learning. And if you ask the question, what's reinforcement learning? The answer that's in the book is all goals and purposes can be thought of as the maximization of some value function. So I'm going to talk a lot about the value function in this talk, just because the reinforcement learning perspective on this involves a value function. Another perspective on it is to think of the problem as we have an agent interacting with an environment in discrete time steps. And at every step, the agent takes an action, receives a reward, and observes a state. And then conditional on that state, based on that state, the agent is going to choose what action to take next. Okay. So for me, what's very interesting about reinforcement learning is that it really combines 3, and in fact 4 learning problems in one. On one hand, we have optimal control, where we're saying we want to maximize value. But that's actually just sort of the center of this puzzle. Then at the same time, we have to do policy evaluation, which I'll explain in a second. And finally, often, because we have this stream of experiences, we'll have to do stochastic approximation. And we have to do these 3 learning problems at the same time as we often have to approximate the function. So this picture is going to come back in the talk. I'll come back to it. But this is the important piece for me today, is that we have all these interleaved problems, and we're all trying to solve them at the same time. Okay, so let me start with some backgrounds I'm sure most of you are going to be familiar with. When we think of this interaction with the environment, we're going to formalize it as a Markov decision process, right? So we have a finite state space, or countable state space, a finite action space, reward function, transition kernel, and then finally a discount factor gamma, okay? And in this setting, a trajectory is going to be a sequence of interactions with the environment, starting in some starting state or maybe some distribution over states, and then proceeding forward in time. In this framework, a policy is a probability distribution over actions that the agent is going to take at any given state, so it's conditioned on the current state. And if the policy is deterministic, then I'm just going to write this as pi of t and drop the distribution, okay? And a transition function then is also going to give us the next state. You'll see there's an emphasis always on sampling things because that's the default mode of operation, okay? So with these pieces in mind, with a transition function and a policy in mind, then we can define a value function. And the value function is the total discounted sum of rewards that we'll observe starting in state X and taking action A. So it's denoted q pi xa, and basically at every time step we're going to transition through the world acting according to pi, transitioning according to p, and then collecting these discounted rewards as we go along. Okay. We can think of this value function as a function mapping state and actions to real values, or we can think of it as a vector in the space of value functions. So when Richard Sutton says, let's maximize the value function, then really what we mean is let's find the policy pi, which maximizes this q pi xa, this value function, pointwise at every state in action. Okay? And this leads, as you well know, it leads to Bellman's equation, which says that the value q pi, we can write it as the sum of discounted rewards, or equivalently we can write it as the immediate reward plus the next state discounted value, okay? So there's the policy evaluation version, which has a pi in the superscript, where we fix pi, and now we just have this Markov chain going forward. And there's the optimality equation, where we take the max over all the actions the next time step. Okay. So in terms of, if we look at the operator that this equation suggests, then t pi is the policy evaluation operator, and it basically maps a q function to another value function according to this formula over here. Okay, and the most important property of the Bellman operator is that it's a gamma contraction. So wherever point we start with in the space, we're going to move closer to q pi. Okay, what that means is that the value function q pi is also the fixed point of that same operator t pi. All right. So there's the policy evaluation operator, and now there's the optimality operator, which instead of taking the expectation at the next time step with respect to the policy pi, let me bring this up quick. So this one samples the next state and the next action x prime a prime according to p and pi. This one will sample the next state according to x prime, but then it's going to maximize the q value of the next time step. And it turns out that this operator is also gamma contraction, although the proof is actually different. It's not the same reason why it's a contraction, but it turns out to both be. They both are contractions. So what's great about this is that then, because it's a contraction, it also has a fixed point, and that fixed point is q star, the optimal value function. Okay, so far things are fairly easy. We understand this world. Everything works nicely. Okay, so if we think about applying these operators or these equations to algorithms, then the natural algorithms are for example, value iteration, where we start from a Q0, an initial value function, and we repeatedly apply the Bellman operator over these value functions. Okay. So that would lead us to a sequence of Q functions, and because it's a gamma contraction, we know that the limit of that sequence is going to be Q star or Q pi, depending. If it's value iteration, it should be Q star. Another algorithm is to do what's called policy iteration, where instead of explicitly applying the operator t to our Q function, we're going to separate the process, the learning process, into two steps. First of all, we look at our current Q function. That Q function is an estimate, if you will, of the total discounted reward that we're expecting to see. We take that Q function and we apply, we ask what's the policy that would greedily maximize the reward I would obtain. Right? So I'm allowing myself to change my one-step decision, and the next time step I have to use the same policy. Okay? So you can formalize this as looking at the argmax over the set of all policies of t pi qk. Okay? So first we find the greedy policy, the policy that maximizes expected value. And then we evaluate this policy basically by fixing pi k, and now we can, for example, apply the t pi k operator repeatedly to compute the value function. So these are the two sort of standard methods of solving these problems if you have a model. There's a third one that's sometimes used called optimistic policy iteration. And in optimistic policy iteration, what we're going to do is we're going to start with a Q0 and look at its greedy policy and do something in between value iteration and policy iteration. So instead of applying the greedy policy exactly once, we'll apply it a number of times and then use the resulting value as our new Q value, qk plus 1. Value iteration is the case where m is equal to 1. And in some sense, policy iteration is the case where m goes to infinity. Okay? So just to go back to this diagram I was showing you earlier, one way to think about policy iteration is we're trying to solve two learning problems, and we're going to neatly decouple them by interleaving them, doing one and then doing the other. Okay? So the first problem is this problem of optimal control, where we're looking for the optimal policy by taking the argmax. And the second problem is to evaluate the resulting policy by running an inner loop where we just, for example, use Monte Carlo simulations to compute these values, or if we have the model, then we run the model. Okay? Any questions so far, by the way? No questions. Okay. Yes.
How do you choose the rule? How do you choose the gamma for the discontinuous?
Very good question. I would take it for granted. I would assume that it's given to me as part of the specification of the MDP. Now, it's true that in practice it's going to depend on your time horizon, and we can get into this in a bit. But gamma is going to affect your approximation error as well, of course, right? But for now, I'm just going to take it for granted. Do you have a suggestion, maybe? How should I take? Okay. So what I want to say is, so far, this was sort of standard, what I would call model-based reinforcement learning, where we assume we can take a state and an action, and we can enumerate all of its successors, or we can sample all of its successors as much as we want. Now, typically, we won't have access to the transition function P, and we won't have access to the reward function. And that leaves us with two options. The first option is to learn a model, to try to estimate from samples P, and to try to estimate from samples R. I'm not going to talk about this today, but I think that's actually a very promising area of research, in the sense that if we need to be sample efficient, we should really be learning a model as opposed to being model-free. The model-free approach says we're not going to try to even estimate P and R. Instead, we're going to learn Q pi or Q star directly from samples. So a way to put it pictorially is, if we think about model-based reinforcement learning, then we start in a state xt, and we can enumerate all the possible actions. Let's assume we can enumerate these actions. And then look at the resulting expectation once we take the transition. Okay. And that gives us these nice contractive properties. This gives us the fixed point fairly easily, and everything is nice. In a model-free case, we're going to have to sample a portion of that tree. Okay. And that's going to reflect a lot more closely the kind of trajectory-based or interaction-based view of the world that we take, for example, when we play Atari games. Okay, so let me start now with model-free reinforcement learning. What's the simplest model-free algorithm? Well, maybe we can still enumerate all the state and the actions. In this case, here's what we can do. We can start in a state and start in an action, and then sample x prime, the next state, a next state, and sample a prime, an action from our policy. We get this sample, and then the SARSA algorithm, SARSA stands for state action, reward, state action. The SARSA algorithm says, start with a Q estimate, QT, and move your Q estimate in the direction of that old estimate. Okay? And the very specific form of this, we can think of it as T hat being a random operator where we apply the policy pi and receive a sample from our environment. So that operator returns a reward R to us, and it returns a next state x prime and a next action a prime. Okay? And then what we get is we're moving in the direction of that sample update. Okay? So one common way that this is going to get written in reinforcement learning is we have Qt plus 1, which is our next estimate, and that's going to be Qt, our current estimate, plus alpha t times the TD error. And the TD error is basically just the difference in current estimate of the value and the sampled estimate. Okay? And in this case, as usual, alpha t is going to be a step size sequence. Okay? Anecdotally, I don't know if you guys know this, but the name SARSA isn't the original name for the algorithm. It was called modified connectionist Q-learning. And there's a paper, I think it's a 95 paper by Richard Sutton, where in a footnote, the paper says, this algorithm is called modified connectionist Q-learning, but it's a mouthful. So we suggest instead we should call it SARSA. And I guess the name stuck. So there you go. So now SARSA is what we call it. Okay, so yes?
The alpha t is adaptive, I mean, here in time, so that's why it depends on time. I mean, you don't take the same step size?
Typically you wouldn't. So to get to proof of convergence, you need to have the usual Robbins-Monroe conditions, or some sort of condition where your step sizes decay slowly enough that you can converge to the point, and yet fast enough that you actually average out the noise. Is it the other way around? The other way around. In practice, we're often going to take it to be fixed, and then we're going to converge to a ball around the solution. Does that make sense? Any more questions? No? Okay. So SARSA uses a fixed policy pi. So the natural sort of pendant of SARSA, we have we had two operators. We had the policy evaluation operator, which kept pi fixed, and we had the control operator, or the optimality operator, which now took a max at every step. So the natural thing to do is we can take that TD error, which is a sample from the policy, and we can replace that sample by a max. So instead of sampling A prime according to our policy, we just look at the next state and take the max. Okay? And that seems like a very, very small change, but it's actually going to affect the whole field of reinforcement learning. In this basic case I'm presenting to you here, it's all fine. So under the Robbins-Monroe conditions, we're going to get convergence in one case to Q pi, in the other case to Q star. But the convergence isn't trivial at all, because now you have 3 learning problems that are being interleaved together. At the outermost level, you're collecting samples from your environment. So you have this stochastic approximation process where you don't actually get to observe the whole model, the whole expectation. And then within that step, you have the steps of policy evaluation and optimal control, where you're trying to evaluate your policy and you're also trying to find the maximal policy. Okay. So this is the case where we can actually sample from the model from any starting state in action. And typically the proofs will require us to do this synchronously from all the state and action pairs at once. Okay. The asynchronous case instead is going to assume that we sample not individual transitions, but whole trajectories from a starting state, but whole trajectories from, for example, a policy and the transition function. Okay. And then we can think of doing exactly the same thing as before, where we're going to apply the update at every step. I think a few of the time indices got left out here. But we apply this stochastic update at every step, except now we have this extra tricky problem that our updates become correlated. So depending on where I am in my Markov chain, I might actually see repeatedly the same state, for example. And this means that the effective step size, when we look at the stochastic approximation problem, the effective step size is going to be depending on how often we visit a state, right? Or how, in other words, the station distribution of that state, okay? So this is, in some sense, the setting that in reinforcement learning we're usually going to deal with. We start in a state, we sample the whole trajectory, and then we try to learn about the Q function using that trajectory. And as I said, the convergence is even more delicate because now we have to contend with uneven numbers of updates to our policy. Okay?
Sorry.
Yes?
Just a clarification. I thought you said that we don't have the transition P.
Yes.
But now you said there that we are sampling from.
You're right. What I meant is we can sample from it, but we might not be able to explicitly enumerate the successes. Effectively, we can't compute the expectation easily. We have to resort to sampling to compute the expectation. In this particular case, actually, we're making even fewer assumptions. We're not even assuming we can reset. Right, so it might be that we have to follow this trajectory. In the other case, we can start in a state, try out a transition, and say, oh, I'm going to reset now and try the state again. In this case, without the reset, it's much harder. Other questions? No. Okay. So just to give you a sense of where the field is at in terms of what do we know, what don't we know, there's a few questions, for example, what are the rates of convergence of this online process? There's been a lot that's been done in this subject, but it's still not quite clear that we have the right rates. An active area of research is how can we actually do variance reduction? So now, once we move to the stochastic approximation setting, we all know that we can often do something better than the sort of naive averaging with a fixed step size or a decaying step size. So for example, Mohammed Azhar had a paper a few years ago where they showed that having 2 copies of the Q value, one which is in some sense is learning the value function quickly, and the other one which is giving us a policy to follow, that you could actually get better rates of convergence, which is quite neat, and better sample efficiency. And then there's a whole line of research on asking the question, if instead of looking at single transitions, we actually back up the discounted rewards from longer trajectories, what we call multi-step methods, then can we still guarantee convergence? And I'll come back to this in a bit to show you what multi-step methods look like. But just to say that even in this simple case, where we can still look at all the states and store their values explicitly, then there's open questions as to how this converges. And finally, last but not least, is this idea of off-policy learning, which often we're going to be able to sample the, from one policy, but then we want to learn about a different policy. Very often we want to learn about the optimal control. And we won't be able to change our sampling distribution. And that's also going to induce some more problems. Okay. So far, what I've talked about is these three circles: optimal control, policy evaluation, and stochastic approximation. And trying to argue that once you interleave these three things, then this gives you the rich reinforcement learning problem, but there's also subtle issues that are going to arise. Now, the deep learning part adds something else, which is what we call function approximation, where we won't be able to represent Q values exactly. Okay? So let me tell you what this looks like. Normally what we're going to do is we're going to say our Q value is parameterized by a parameter theta. And when we do learning, we're also going to now bring in a projection step back into the space, the parametric space of our value functions. So that projection step is pi, and effectively what it says is, in its simplest form, we'll apply the Bellman operator and then project the result of applying this Bellman operator to a value function Q back into the space of functions we have. Okay? And so this sort of hand-drawn diagram shows this to you. You have Q, you start in Q, you go out of the subspace with TQ, and then you have to project down. And this error that you get from going from TQ to the projection is actually going to compound as you apply successive steps of that process. Okay? And it's bad enough that it can actually cause divergence. So as soon as we move to the approximate case, we're no longer guaranteed to converge to a fixed point. Okay? There are some classic results that show that that's not always true. So sometimes we can converge. So I just want to point out, probably the most famous one is the one by Tsitsiklis and Van Rooij that said that if the approximation is linear, so we have some basis functions, phi of xa, and we define the value to be a dot product between a parameter vector theta and phi of xa, where phi of xa is some vector, some real valued vector, then SARSA will actually converge. And SARSA will converge to a Q hat, which is the fixed point of this equation here. Effectively, not too surprising, is the fixed point of the operator which first applies the Bellman operator and then applies a projection step. Okay? And now the error of SARSA is actually going to be bounded by a factor of 1 over 1 minus gamma times the best error you could have if you directly knew Q pi. So put another way, if you knew the real value, you would project it directly into your support, and that would minimize the error. Now, by not being able to directly minimize project this value function, because we don't know it, so we have to interleave approximation now with learning, then this adds additional error. Okay? The convergence proof for SARSA is actually in a norm that depends on the stationary distribution of the process induced by pi. Once you move to Q-learning, then things might diverge. Because as you change your policy, you're actually going to change the stationary distribution underlying the Markov chain of the process. Okay? And that's actually still an open question as to how we should fix that control issue. There was this whole line of research from 2009 to 2013 on trying to get convergent linear time optimal control. And by this I mean an algorithm that would run in a time linear in the number of features in the linear approximation case and would still converge. There's been a lot of promising results in that direction, but it's still an open area of research. Another question we've looked at is how to actually explore under function approximation. So by that what I mean is, now that we have this idea of an approximate value function, we might not be able to change the policy as we see fit and sample actions as we see fit. We might be stuck with a policy, for example, which is greedy with respect to the value function. I won't talk much more about this today except to say that it's choosing the right policy to sample from is an important issue in reinforcement learning. Okay. And finally, the multi-step extensions I've already mentioned now in the approximate case don't usually converge. And there's actually some very, very recent work showing that algorithms that are very robust in the tabular case, when we can represent the value function exactly, now stop converging in the approximate case. All right. So what I've done so far is started with this very ideal case of having the Bellman operator and applying the Bellman operator to find the fixed point. Oops, I've lost a piece of it. To the practical case where now we have these very large state spaces to deal with. We don't have access to the model, but we need to do something. Okay, and this is going to take us to the deep learning part. Okay. So if we go back to these games I was telling you about earlier, it turns out that for many of these games, linear approximation with some sort of reinforcement learning method has had some good success. So Samuel's checker player was actually using linear approximation. And that conversion, he could play checkers. There's actually a lot of work on Go and also on the Atari, for example, that use linear approximation. I'm using these. There's many examples of successful linear approximation schemes for reinforcement learning. But now, what happened over the last few years is people realized, or re-realized, if you will, because we knew this already, the power of neural networks for approximating these value functions. Okay, so deep learning, in other words. And as I said earlier, this started, or the explosion happened around 2011, 2012, when people realized that a very simple neural network could achieve better performance than very complex vision architectures. So this got started in vision. It makes sense that if the successes were in vision, that they should first sort of be applied to games with a vision component, like Go or Atari, for example. So if you're not familiar with deep learning, the basic idea is to say we have this feature map, phi, but now we're going to parameterize it by a parameter theta. And we're going to learn that feature map. So instead of taking it to be fixed and only learning the last part, which would then be our parameter theta, we're going to learn the whole thing. Both the last part, which is linear, and the rest, which gives us the feature. And the way to do this is to define a loss function, L theta, and then do gradient descent, very simply, gradient descent or some variation of gradient descent on that L theta. Okay. This is actually the network that was used in the Atari playing agents in 2015. So you can see it's actually a fairly simple network, right? The very last thing before the fully connected layer of rectified linear units, that's the phi. And before then, we only really have two stacks. I guess I should say these are stacks of nonlinear transformations called convolutional filters. And then we're taking as input raw images, in this case, raw Atari frames, and map these raw Atari frames to the phis. Right? So it's actually pretty surprising that just by doing gradient descent, you can actually get reasonable features phis out of this. Okay. Yes?
Here represents what?
Sorry, say that again?
But I mean the action.
A in this
This
case.
So you're saying where is the A in the actual network?
Yes.
That's a very good question. In this case, I guess I did lie. You're right. In the case of this particular network, the A is only at the last. So each action has its separate set of weights.
Sorry.
Each action has a separate set of weights that we're going to take the dot product with. So the phi is shared between all the actions. It's effectively phi of x. And then we take the dot product between phi and a theta A.
So A is like a state variable.
I'm mostly looking at discrete.
You enter it in the inputs, in fact, or no?
In this case, the action is discrete. So we just enumerate it. We just make copies. You can think of it as making copies of this phi vector. We have 18 actions, for example. In the case of Atari, we would make 18 copies of that action that vector. Okay. If A is a continuous control, then that approach isn't going to work, right? And maybe that's the case you're thinking about in the continuous case. In the continuous case, the two approaches is to feed it in as an input, as you say, or typically what people will do is to output a parameterized policy. For example, the simplest case would be to have a Gaussian with a mean and a standard deviation, and then we would output the parameters of that Gaussian, right?
Okay. Thank you.
You filtering it.
What was that?
Filtering.
No, it wouldn't be filtering because even in a continuous case, you're still trying to learn the Q value. You're still trying to learn the value function that's associated with this output.
Sorry, what about the function L? How do you decide?
Let me show you what the function L looks like. So in this deep Q network architecture that I was just showing you that was used to play Atari games, the function L is the squared loss, the expected, the mean squared error between the what's called the target and the current output. If you look at it, this should look very familiar to the TD error I was mentioning earlier, because it is. So we're looking at minimizing the square TD error. Okay. The main reason for this is because we can take the gradient, it's going to be a very nice gradient. When we differentiate this function, then we're going to get the TD error times the gradient of the Q value itself with respect to the parameters. Okay. To this day, this is almost always the function that's used in these kinds of deep networks. Does that answer your question?
Yes.
Okay, good. Now, if it turns out that if you just do the procedure I talked about, that doesn't actually work. Okay. So remember how I've been telling you how as you move away from the Bellman operator and into a more stochastic regime, convergence becomes less and less stable, right? Well, it turns out once you move to Q-learning with a deep network, that's bad enough that now the simple approach just diverges. And the early work we did with this setup, the value function would just diverge to infinity, and then nothing interesting was happening. Some of the issues that arise because of that sequential nature, that the fact that we're dealing with trajectories. So the data is sequential, which means that the samples we're learning from are not IED, and that's actually enough to prevent us from learning the right representation, if you will. Another issue, and this is related to Q-learning, is that as our Q value is changing, the policy itself is going to change very rapidly, and that, for the same reason it fails in a linear proximate case, that's also going to fail in a deep network case, where we're going to get these oscillations and extreme data distributions. Okay. And finally, this is more specific to Atari, but there's also the issue that we want to design a network that's going to be robust to the scale of the rewards and the scale of the Q values. And there's a big issue in deep learning with the fact that naive gradient descent doesn't work. You need to then scale your gradients down, for example, using a second order method or an approximation to a second order method. And the scale of the rewards plays a big role in making things more unstable. Okay. So I want to tell you just a few of the tricks that have been used to make this deep Q network work in practice. And these three tricks are experience replay, target networks, and reward clipping. So experience replay is very simple. The idea is we're going to try to break the correlations, so move away from this trajectory and more into an IED setting where we can update from IED samples. Okay? The target network is going to be there to keep the target values fixed for a while. That's going to avoid oscillations, and then the reward clipping is very simple. Okay, so let me start with experience replay. What we do is, as we're experiencing these trajectories, instead of applying this asynchronous update at every step, we're going to instead build a data set D. Okay? In this case, we're going to assume we're going to follow some policy that's reasonable, for example, an epsilon greedy policy. We store all the transitions in what we call a replay memory. Okay? And then the loss function will become the expectation of under that data set, where we sample transitions from that data set and then try to minimize the mean loss with respect to that data set. What that does is basically now completely decouples the data collection process from estimating the value of that policy. Okay. Now that doesn't actually fix the optimal control issue, which is that the policy changes. So to avoid that issue, the trick is to fix the parameters of the target loss, of the target in the loss function. So what that means is we're going to compute the target part of the TD error using an old set of parameters, theta minus, okay? And then we're going to define our loss to be with respect to these parameters. So there's a big difference here now that we have the parameter theta, which we're actually optimizing over, and then we have this theta minus, which is effectively a fixed target, as long as we don't change those weights. And what we're going to do is periodically update this target network. Now, what I want to say is that these two tricks, if you think about them, are very similar to the old approaches from reinforcement learning. So the target network is effectively doing policy iteration of a kind, where we, instead of doing value iteration, we try to keep doing the max at every step, or Q-learning, then we try to learn the value of a policy by keeping that policy fixed for a while, and then move on with the next policy. The same way, experience replay is like building an empirical model. So we're going to try to move away from the completely asynchronous case and back into a regime where things are a bit more stable, right? So for me to get things to work, it's always trying to bring things back to the Bellman operator that we know works and that we love so much. Okay, the reward clipping, it's not so important, but basically we just take the reward function. This is, again, fairly Atari specific, but clip it between the range -1 and 1. And one thing that this does that's very interesting is, in early experiments, what we saw was the values would be overestimated. So what do I mean by this? Well, if you take any sort of approximator, a value approximator, and you fix a policy, the greedy policy with respect to that value function, then you can ask the question using Monte Carlo samplings, are you being truthful? Are you telling me the value you think you're going to achieve, is that actually achieved by your policy? And what you see is that consistently the values are overestimated. Very rarely are the values underestimated. This has to do with the fact that we're taking a max at every step. This has a number of other causes. But one way to deal with this or prevent it a bit is to have smaller gradients. So I won't talk much more about this, but we can talk about it afterwards if you want. One bad side effect is once we move into that domain, we're not even really solving the right control problem anymore, because now we've truncated our rewards, so we can't differentiate a large reward from a small reward. But these are the sacrifices we have to make sometimes. So just to give you a sense for, do these heuristics matter? The answer is yes, they do. So these are scores taken from 5 different Atari games. Breakout, the names don't matter too much, but Breakout, Enduro, River Raid, Sequest, and Space Invaders. And what you see is that it's very clear that as you add these heuristics, the scores, the performance effectively goes up quite dramatically. So without these tricks, the deep learning approach for reinforcement learning doesn't really work out of the box. Since then, there's actually been a lot of work done in trying to understand whether these things can be overcome. Can we deal with them? I won't be talking about this today, but there's recent research you can look up on. So, unfortunately, this is a PDF, so we'll only have the still to look at. What I was going to show you is very simply, this is a game called Space Invaders, and it's pretty amazing to see these agents play the game after. We'll train them for maybe, usually it's 200 million frames, which admittedly consists in playing the game nonstop for 36 days. But this point aside, we're more sample efficient now. They'll train nonstop for this amount of time, and then the policies that emerge are actually surprisingly human-like. And so it's quite neat to watch to see the agent sort of plan its way through. So all this to say, there is actually a lot of power in these deep networks in terms of the kind of value functions they can represent and the kind of policies we can then extract out of these. Okay, so I'm right on time, so I'm just going to tell you very briefly about some of the more recent research that we've done. This is going to be quite compacted, but just so you don't leave with the idea that we apply Q-learning with the deep network and we're done. Some of the active research that's going on is this idea of, coming back to this idea of off-policy, which is very often, on almost all settings, we'll have a lot of old data generated from a policy mu, or many policies, including if we use the experience replay, we'll have this effect of having old data. And what we would like to do is estimate the value of a different policy. For example, the control policy, okay? And we know, as I've mentioned already, that the naive approach will diverge with function approximation. So there's a question of how can we actually correct for this discrepancy between pi and mu. One thing we can do is we can use importance sampling. Now, in practice, importance sampling, the naive version has far too much variance, and it doesn't really help us, okay? Another issue is that we might want some safety guarantees. So we have this old data. We don't know if it's good or if it's close or far from the policy pi. So there's actually an interesting line of work by Philip Thomas and Emma Brunskill and others in asking the question, can we actually guarantee a performance based on old data? Okay. Some research I was involved in recently is this idea of looking at multi-step methods. So you have the equation here. In a multi-step method, instead of looking at just a one-step update, where we look at the next state transition and take the Q value at that next state, we're going to allow the process to roll a few steps forward, actually K steps forward, and then truncate it and look at the Q value K steps in the future. And up to that point, we're going to sum up the rewards, the discounted rewards. Basically, the case K goes to infinity is the Monte Carlo rollout for that value. And it turns out that it's well known that we get much better accuracy if we, instead of using the one-step return, where we truncate immediately after one step, we use multi-step returns. And the typical algorithm for this is called TD lambda, or just the lambda operator, which is going to mix in, using a geometric mixture, these different lengths of rollouts. Okay? So you can either write it in this form here, where we explicitly have this mix-in. It actually doesn't normalize to 1. That's okay. We're also happy with that fact. The alternative form is to write it as we take our Q value and then we update it by a mixture of TD errors, where the TD errors are different time steps. Okay. So now we had an algorithm recently called retrace lambda, which is actually both safe in an off-policy sense and also multi-step. And some surprising results that the convergence proof is not trivial. So even without function approximation, once we move to this slightly more complicated case, there are corner cases where the dynamics of the system will not get us to converge. So this is still an ongoing area of research. Another interesting question is whether we can devise alternatives to the Bellman operator that might have better guarantees or better properties in practice. So one of the things we looked at was this idea of a gap increasing operator. The action gap is the difference between the max value you could get, so the max over all the actions at that state, minus the value of another action, okay? So if two actions have exactly the same value, then the gap is 0. If an action is much worse than another action, then the gap would be quite high. And it turns out that the Bellman operator is not the only operator that will give us good behavior or good Q values. And so we looked at these. There's actually a family of operators that are convergent. A subset of these are what we call the gap increasing operators. And what they do is they look at the Bellman operator here, and they subtract the current action gap. Effectively, it's a bit like doubling down. They say, I'm going to take my usual Bellman operator and increase the gap. All the actions that I think are suboptimal, I'm going to make them even more suboptimal in terms of my estimate. Okay? What's very surprising about this is that these new operators aren't contractions anymore. So we can't guarantee that we converge just based on a contraction property. And actually, the suboptimal Q values might not even converge. But we actually show that under certain conditions, including beta being smaller than 1, then the limit of that process will actually converge to Q star for the optimal action. So you have an operator that's going to preserve the optimal value while increasing the action gap for the other values. All right. So I'm going to conclude here just to bring up that picture again and to say, my perspective on reinforcement learning is that it's this interleaved learning process. And it's super interesting, I think, to start sort of poking at the different pieces and saying, you know, how can we make things more stable? How can we learn more efficiently? And of course, how can we apply this to something like Atari games? So hopefully this was enjoyable, and if you have any questions, I'll take them now. Thank you very much.
Okay, so thanks very much, Marc, and yeah, we'll open up to questions.
Okay, just to check whether I understood properly, the multi-step is the equivalent of what is known in regression Monte Carlo literature as Longstaff-Schwartz algorithm.
I'm unfortunately not familiar with that, so I couldn't tell you.
Then we can discuss.
Yes, we should.
I'd like to know what to do if you have now two players playing against each other.
The short answer is you shouldn't use Q-learning. Well, we know that these algorithms don't have regret minimization properties. So if you have two players, for example, the safe solution should be to actually, I'm going to take it back. I believe in the case where full information, you can still use Q-learning. But in general, if your optimal strategy is a mixed strategy, you couldn't use Q-learning, right? In the case of Go, I don't actually have I don't know if that result is true or not, if you can use Q-learning directly. That's a good question. Normally, I would say for two players, as soon as you have partial information, then you should use something like regret matching or hedge, which would actually guarantee low regret. But I don't know if you had a more specific question in mind.
No. Two players, and of course then infinite number of players. So many. You are playing, so okay. Like I'm thinking of video games where you are playing in networks, so you don't know how many players are around you, and you try to learn automatically, please.
I think that's a very interesting question. I think the floor is still open as to how to solve these questions. I think one important question is whether the dynamics are stable between all of these learning processes. In the case of something like Go, even then, once you bring in approximation, there can be an issue where both players could learn to play a subset of the whole state space, at which point there's no guarantee as to how they perform elsewhere, right? So once you go to infinite number of players, I don't even know how to, but this is very interesting. Yeah.
So other questions? I had one. So what if, say you change the rules of your game halfway through, so I think say in your Space Invaders game suddenly you drop a block so that your spaceship can't move anymore. How easy is it? Will the computer game, will the agent then adapt quicker to the new setting, having already learned the old setting?
Absolutely not. So I think that's a big flaw of these methods, that you learn a value function, and that value function tells you how good the world is going to be, and then usually you'll have a policy which maximizes that value. Now, that function is learned from slow, repeated iterations, right? Typically involving, for example, in this case, the experience replay. So there's no easy way to adapt. And I think that's actually an open question, is how to design a reinforcement learning algorithm that would be adaptive in this kind of way. Some people might say, well, the simple solution is to have a value function which includes variations of the environment. But I think the case you're saying is this is something the agent has never seen, right? Never. And in this case, there's no good solution yet, I think.
I have one more question.
Okay.
Can you explain to us then, going from games, saying, to wind farm control or something more economic, how would you use these kind of approaches?
What do you mean exactly?
So where you don't have pixels anymore, but
yes, I see.
How would you control a wind farm with this kind of
I see.
power plant?
I think to some extent, so the basic, in the case of the pixels, the additional piece we know is that we know how to deal with vision. These convolutional networks have proved really useful. Basically, leveraging signal processing, leveraging a lot of literature. These convolutional networks are really good at processing this information. Once we move to something different where the input space is no longer visual or audio, then I think the question is, do we have the right features, or will the deep network learn these features? I think so far it looks like we can also. Now, for example, there was some work by my colleagues at DeepMind where they actually were optimizing not a wind farm, but the cooling system inside a data center. And they were very successful with that approach using reinforcement learning, even though there's no pixels involved, right? And
Thank you.
So another question is, so in the game you are showing us, we can see that you have the score, which is displayed. So I guess this is a good proxy of the value of the frame. And all those games like this, or do you have all those techniques also work if you have no scores?
that's an excellent question. So actually, the game that's displayed here, Pitfall, is an interesting example because the score is mostly you lose points. You very rarely gain points in this game. At the moment, there's very few reinforcement learning techniques that deal with these kinds of problems. Where, in a sense, we're moving away from the Markov decision process framework, where we assume that there's a clear objective to be maximized that's given to us and easily read out, to a setting where we're asking, well, what will the agent do in the absence of this signal? One solution might be to look at something like what we call intrinsic motivation, where we say we're going to try to come up with their own reward signal that would cause the agent to have a behavior that's interesting. I've done some work in that direction. I've actually, we had a few papers recently on using probabilistic models of the images as a proxy for driving intrinsic behavior. But it's sort of an open question as to how to best do this. Any more questions? No?
Okay, I've seen that these models are can be, I think, generalized to a lot of settings. So, for example, I was thinking about financial setting, gain setting, and so on. So do you have general rules which, in your experience, this approach works or doesn't?
I think the thing to remember with deep learning is often success comes after a lot of engineering. So far, they've proven surprisingly powerful in a number of settings people would not have expected. I think people are asking the question, why is there a property of these kinds of networks that make them good? Right? So if the learning problem was convex, then we would all understand it's because we're doing stochastic gradient descent and then we're just finding the minimum of that convex function. So the big question mark is we know that there's a lot of representation power in these networks. There's actually results showing you can overfit these training sets for machine learning problems to get zero classification error. And yet, the overfitting doesn't seem to hurt us when it comes to test time, right, or generalization time. So that's the surprising part, is that the optimization procedure doesn't seem to hurt performance too much, and the fact that it's non-convex doesn't seem to be an issue either. Now, there might be problems. There are papers trying to say, well, these problems we can't solve with deep networks. They tend to be more synthetic. And I think it's a very interesting question, open question, whether there are problems where it's not going to scale up. I think sample efficiency is an important part. Because as I was saying, 36 days is too many days. And if on a 37th day, then there's a block that falls on your screen and you have to restart this process. That's clearly something we need to figure out, how to solve that issue. Thank you.
Okay, so I think at this point let's move further discussions to after the talk, to a more free setting, and let's thank Marc again.